Good evening, High Legh. A pleasure to be back again, this time telling you about cosmic rays. So for the last half hour or so, I've had the cloud chamber running at the bench here at the front of the room, and we're seeing cosmic rays every once in a while. There we go, there's one on the left-hand side. If we wait a few more seconds, we might catch another one. There was a little electron, for instance. And I'll be telling you about the cloud chamber and about what else is on this front bench in due course. So let's switch from the live demo for the moment back to the PowerPoint. So I'm going to give you a little bit of an introduction, and then before launching headlong into cosmic rays, I'm going to give you a little bit of background, because I figured that thinking about radiation from the cosmos, perhaps it's worth putting it in context about radiation from a little closer to home, radiation from the Earth. Then I'll be describing cosmic rays, the history of cosmic rays, a little over 100 years old now, as in terms of our understanding of them. I'll say a little bit about the detectors that we use to look at or study or observe cosmic rays. And then I'll be asking the question, okay, where are these cosmic rays actually coming from that we observe here on Earth? And then I'll summarize right at the end. Yes, the HLCO lawyers insist that I have a risk assessment, and yes, it's available if anybody wants a PDF copy. I have on the front bench here some radioactive samples, perfectly safe. I will use them for the demonstrations, and then I will put them away if anybody wants to approach the bench at the end of the talk for a closer look at any of the equipment here on the front. I've got a Geiger-Müller detector, the yellow box here, and I've got a cloud chamber, which is a cloud chamber I built and tested on my kitchen table. If anybody's interested, I've got the instructions to how to build one for yourself on the side here. So let me start with the Geiger counter. So I guess you can just about hear that. I know it's not particularly loud, but if we switch a Geiger counter on and keep any radioactive samples away, we still get a little bit of clicking in the background radiation. Each click that you can hear signals the arrival of a subatomic particle passing through the detector. Everybody calls them Geiger counters. Physicists get a little bit irate at that because they really should be called Geiger-Müller detectors, but okay, everybody calls them Geiger counters, so let's stick with the common name. But what is each click? Where are they coming from? Well, each click might signal a particle traveling through the detector that came from an atom lurking somewhere in this room. Or each click might signal the arrival from much further afield. Perhaps it was the result of a supernova that went off in a galaxy far, far away. You can't tell from the clicks. A Geiger counter is great for telling you how many things, how many particles pass through the detector. It doesn't tell you what they are. So it's great for giving you a count, not so good for telling you what they are, which is why we have different detectors for different purposes. So, okay, the clicking is going to get annoying after a while, so let me just switch that off for the moment. So we have to remind ourselves, radiation is around us all of the time. It's something you have lived with all of your life, and it's not necessarily something to be worried about. Remember, the Earth is a radioactive planet. That's just a fact of life. It's nothing to do with what we have done, man, in terms of setting off bombs. It is a radioactive planet. It was radioactive when it was made 4.5 billion years ago, and it's radioactive today. That's a natural consequence of the properties of some of the elements that make up the Earth. If we have a look at the periodic table of the elements, there they all are. Some of the elements in the periodic table are stable. In other words, once an atom has been made, apart from maybe stripping a few electrons off or adding a few electrons in, once the atom has been made, the atom is essentially unchanged forever. But there are some elements in the periodic table that are unstable. They change. Physicists call it decay, not as in they go mouldy, but change into something else. One element changes into another element. So physicists talk about an element decaying into another element. So some elements are unstable, and when an element changes from one element to another, it spits out something. Let's have a look at an example. Let's have a look at a piece of uranium. So switch to live video. So let's switch back to the camera. And let's switch away from the cloud chamber to a piece of uranium. Now this is a piece of glass doped with uranium. Nothing special about it particularly. Why do you put uranium in glass? Well, not because you want your glass cabinet to be radioactive. People put uranium in glass because it fluoresces and it looks quite pretty when you illuminate it with ultraviolet light. So just for the purpose of anybody watching the video, I've just demonstrated that under UV, it fluoresces like mad. But that particular piece of uranium glass is a little bit too big to put into the cloud chamber. So what we're going to do is, let me just convince you that it is actually radioactive. Let me keep the Geiger counter on for the moment and just put it in there. It's not particularly radioactive, but it is radioactive. A bit too big for the cloud chamber, so I'm going to pick a radioactive mineral. It's only a few millimeters or so in size, but this is more radioactive than the glass I was just demonstrating. I can prove it's radioactive. You can see its size. It's barely a few millimeters in size. Quite definitely radioactive. What I'm going to do is put it into the cloud chamber. That means I have to disturb the cloud chamber, having carefully set it up so that the temperatures are right. I'm now going to disturb it, and hopefully it will settle down again reasonably quickly. Let me just put that away, and let me avoid listening to the clicking forever. So I've now put a radioactive sample inside the cloud chamber, and having disturbed the nice formation of clouds, it's going to take a little bit of time, and I'm going to slowly waffle until it decides, oh, there we go. Have you see that? So this radioactive sample is spitting out something. You can tell what you're looking at is not cosmic because all the lines you're going to see all trace back to the radioactive mineral. It's a radioactive mineral that contains a little bit of uranium. It's actually a very small percentage of uranium. It doesn't actually matter what this is. But notice that we can see quite definitely this radioactive mineral is spitting out something. In other words, a cloud chamber allows us to see radioactivity. Perhaps you also notice, after perhaps a few seconds, perhaps a few minutes, notice that what is getting spat out falls into two different categories. Perhaps you can see that. Sometimes it spits out something which has a very narrow, very precise path, and occasionally it spits out something which is a little more ghostly, a little broader, a little less defined. Yeah? So we can say, A, something is coming out, and whatever is coming out of this mineral falls into two particular classes. And in good Blue Peter fashion, just in case the cloud chamber didn't work too well, I recorded a different mineral in the cloud chamber. So I have absolute faith in this cloud chamber, but just to be on the safe side, this is another piece of uranium mineral. And again, we can see that different stuff is coming out. If I take not a video, but I take all the frames of the video and add them all together, it's even more clear, I hope, that we have quite definitely some very thin tracks and some rather broader, less defined tracks. It's almost like they're smudges in the background. So the rock is clearly emitting something, whether it be the live demo we've just looked at or this pre-recorded mineral. Something is coming out. The particles that are leaving tracks in the detector, there are clearly two types, and we can ask ourselves where they're coming from. So we need to think about atoms. Now, this is how we tend to think about atoms, a positively charged nucleus and negatively charged electrons buzzing around. It's not a great model for what an atom is, but it will do. It's good enough for our purposes to get an idea of what's going on. It is the nucleus alone, regardless of whether we're looking at electrons or not, it is the nucleus alone which determines whether or not an atom or an element is radioactive. It's got nothing to do with the electrons that are buzzing around the nucleus. And this is a little bit complicated. This is basically saying, what are the possibilities if you have a very heavy nucleus, a very heavy element, like, for instance, uranium? What can that nucleus change into, and what can it spit out in order to change into something else? We're not going to go through all the possibilities, but just to make it clear, there are lots of possibilities. A nucleus might spit out a proton and change into something else. A nucleus might spit out a neutron and change into another, not another element, but a different version of the same element. It's also possible that a nucleus might spit out a combination of protons and neutrons. It just so happens that the particle, which we call an alpha particle, comprises 2 protons and 2 neutrons. It just happens that that is a very stable structure, and so it is very common to find 2 protons and 2 neutrons together. So at the time it was called an alpha particle. It wasn't clear whether it was a fundamental particle, but it turns out it's actually made up of other stuff. And sometimes nuclei can spit out these particles. It's also possible for a nucleus to spit out an electron, as indicated on the left-hand side there. But it's also possible that a nucleus can spit out the antimatter equivalent of an electron. Every particle has an antimatter equivalent. A proton has an antiproton as an equivalent. An electron has an anti-electron. So we either call it a negatively charged beta particle, because beta rays, they didn't know they were electrons in the first place, and they simply called them beta particles or beta rays. We now know that those are electrons, and the antimatter equivalent of an electron, you either call it an antimatter electron, or for convenience, it's given the name positron. It's also possible that a nucleus, when it wants to change or lose some energy, might spit out a gamma ray. So we're not going to go through all of those possibilities. I'm just reminding you that nuclei can do lots of complicated things. When it comes to understanding what we need for the cloud chamber, we really only need to look at 3 possibilities. And you probably remember these when you're dealing with radiation, especially at school. You get taught about alpha, beta, and gamma radiation. So alpha rays or alpha particles, historically they were called alpha rays before they worked out, are they electromagnetic waves like light, or are they actually particles of something? So in this talk, I will always use rays and particles interchangeably. In other words, alpha ray is the same as alpha particle. It's only history that attempted to differentiate, and the wording changed slightly. So an alpha particle is 2 protons and 2 neutrons. They're quite heavy because it's 4 particles rather than something a lot lighter. And alphas cannot travel very far. So for instance, alpha particles cannot travel through the glass of this cloud chamber, whereas other particles can. For instance, beta rays, originally didn't know what they were. We now know they're electrons, or the antimatter equivalent of electrons. They are very light. An electron is thousands of times lighter than a proton, so many thousands of times lighter than an alpha particle. And if they have the right amount of energy, they can easily penetrate material like a thin sheet of metal or a piece of glass. The gamma of the alpha, beta, gamma is different from alphas and betas because it is a real ray in the sense that it is electromagnetic radiation. It is a wave. Yes, you can always think of it as a particle if you think about a photon of gamma rays, but it is rather different from the alphas and betas that we've got there. It is not a charged particle, unlike alpha, which has got a charge of 2, and beta, which has got a charge of +1 or -1, depending on whether we're dealing with electron or positron. Gammas do not have charge, and they do not leave tracks in a cloud chamber. So they might produce a click on the Geiger counter, but we will not see gamma rays through our cloud chamber. So when we go back to our camera and look at what we've got there, we now recognize that we're actually seeing alphas and betas. Remember, we won't see gammas, and take it from me that this particular sample will not produce a lot of other exotic particles that it spits out. So it might in principle be producing alpha, beta, and gamma, but we're not going to see gamma, and we're left with alpha and beta. So betas are the very narrow, very well-defined tracks. They are electrons, and the rather broad bulldozer tracks that we get are the alpha particles. They contain a lot of energy, they produce a very broad track, they produce a lot of damage, if you like. They end up ionizing a lot of the molecules that are inside the cloud chamber, and that's why they produce a much broader track. Now I'm going to want to go back to cosmic rays in a little while, so I'm going to take the particle of uranium out so that the cloud chamber has a chance to recover for later in the talk. Let me put the sample away before I lose it. Okay, so let's go back to the PowerPoint. And again, now that we understand what it is we're looking at, we recognize that we're looking at alpha and beta. The beta particles, the very narrow tracks, the alpha, the very broad, rather more ghostly tracks that we can see there. Now, in terms of making sense of radioactivity, it's also worth noting that different elements can come in different varieties, cousins, if you like, of the same type of atom. So, for instance, if we think of carbon as an example, a carbon atom has 6 protons in the nucleus. That's the definition of carbon. An atom with 6 protons, number 6 in the periodic table, is what we call carbon. So any nucleus which has 6 protons is by definition a carbon nucleus. If it also has 6 neutrons, then that is a stable so-called isotope, a cousin of other carbon atoms. It's a stable isotope, and we call it C12 simply because it has 6 protons, 6 neutrons, total number is 12. We call that carbon 12. And most of the carbon in your body is carbon 12. But carbon comes in other flavors. It has a cousin, which also has 6 protons by definition, but it's also possible for carbon to come in a variety that has 8 neutrons. And so, not surprisingly, we call that carbon 14, 6 protons plus 8 neutrons, 14 in total. Carbon 14 is the radioactive carbon that we use in radiocarbon dating. If you want to tell how old a tree is and you think it's a few thousand years old, if you can get hold of any organic matter, then you look at how much carbon 12 you've got, how much carbon 14 you've got. We know the half-life of carbon 14, so we can tell when this particular organic matter died. It's continually taking in carbon 14 from the atmosphere until it dies, and then the carbon 14 decays away with a particular half-life of quite a few thousand years. So we use carbon 14 for radioactive decay dating. Where does the carbon 14 come from in the first place? I'm getting a little ahead of myself, but actually carbon 14 it's produced in the atmosphere by cosmic rays. In other words, radiation on our atmosphere actually makes carbon 14, and that's how we use carbon dating. Just a little bit about other radioactive elements, especially ones in your body. Potassium is the most abundant of the radioactive elements. You perhaps don't think of potassium as being a problem in terms of radiation, because you know that there's lots of potassium in you and there's lots of potassium in your food. If you work out how much potassium there is in your body, then probably 4,000 potassium atoms per second are decaying and changing into something else. And if 4,000 atoms sounds ridiculously high, 4,000 atoms per second, remember there's an awful lot of atoms in your body. So it's actually an absolutely tiny amount of potassium. But it is one of the largest contributions to natural background radiation. Thorium is more abundant than uranium, and uranium is more abundant than you think. Those are the 3 most abundant radioactive materials. Most people are surprised to realize just how much uranium there is in the Earth's crust. 3 parts per million, 500 times more than the amount of gold in the Earth's crust. So an absolutely huge amount. It's only a question of how difficult it is to dig up. Gold is easy to dig up because it exists as a metal. With uranium, it exists as an oxide and you've got to purify it, etc. In the Earth's core, these radioactive elements in the Earth's core are emitting energy because they are decaying and spitting out various particles which have a certain amount of energy, and that is keeping the Earth's core warm. The Earth's core is molten not because of any radiation coming from the sun, but because of the radiation internally coming from these radioactive elements. So it's interesting to note that radioactive decay in the Earth's core is keeping the core molten, which gives us a dynamo, which gives us a magnetic field, which partly protects us from external radiation. So there's a sort of cycle of life here. Radiation is actually responsible for shielding us from some of the radiation from the sun. Not from all cosmic rays, but from some of the low energy coming from the sun, our magnetic field protects us to some extent. And just as a little bit of a side, let me come back to antimatter. A small fraction of potassium, an isotope of potassium called K40, actually emits beta plus radiation. Remember, beta minus is our familiar electron. Beta plus is the antimatter equivalent of that electron, a so-called positron. So potassium-40 emits antimatter, and hence foods rich in potassium emit antimatter. That means Brazil nuts, bananas, various other high-protein foods are antimatter emitters. That gave rise to the banana equivalent dose. For those that wanted to actually say, well, what is this radiation? It's rather a low level. How can we compare that? Well, we can't compare it with the output of a nuclear reactor. Let's compare this low-level dose with something equally low. Let's pick bananas. A banana emits a certain amount of radiation, so somebody had the idea of defining the banana equivalent dose. If eating one banana is the banana equivalent dose, then what, for instance, is the dose that you are currently getting per day? Everybody in the world, pretty much independent of which part of the world you live in, everybody receives a certain dose of radiation from cosmic rays. What is that in banana equivalent dose? Well, it's equivalent to something like 2 hands of bananas. In other words, the amount of radiation you receive from the cosmos is roughly 10 times as much as you receive if you were to eat 1 banana a day. Bear in mind that you'd have to adjust that if you fly a lot, because if you fly a lot, you receive a larger cosmic ray dose, which is why pilots have to be careful as to how many hours they put in if they're doing transatlantic flights, for instance, and spending a lot of time at altitude. One final point before we move on from terrestrial radiation. Radon is a gas that emits alpha particles. Not all radioactive elements are in solid form, such as uranium and minerals, etc., that we're used to, but radon is a radioactive gas which is formed by the decay of small amounts of uranium. And uranium exists naturally in pretty much all rocks in tiny amounts, and in particular uranium exists in granite. So if you live in an area where there's a lot of granite under your feet, that uranium in the granite will produce radon, and that radon as a gas will bubble to the surface. Not that much of a problem in Cheshire. When we look at a radon map, red is particularly high in radon. You notice that's where granite tends to exist in the UK. So certain rocky formations like the Pennines, and especially the southwest of England, Cornwall, etc. Here in Cheshire, you can see where we are on the map. We're about as low as you can get. That doesn't actually mean zero, but there's not much radon around in this part of the world. So if we took a Geiger counter or a cloud chamber down to the southwest of England, we'd see a lot more radon. And radon emits alpha particles, and we would see the alpha particles in the cloud chamber, and we would hear a slightly higher click rate if we went down to the southwest of England. Okay, that was my background, making sure that we're all familiar with the concepts of terrestrial radiation before we get stuck into cosmic radiation. So these are the key players. You might recognize some, but I'm guessing you probably don't recognize all. I think most of you would recognize Marie Curie in the middle there. Some of you might recognize Henri Becquerel on the left-hand side, who basically discovered radioactivity. Marie Curie then took some of those observations of radioactivity and started synthesizing different elements such as radium and polonium, etc. But perhaps Victor Hess is a name that you're less familiar with. Let's see how he comes into the story. In the late 1800s, it was known that there was background radiation. People had little electroscopes like this one, gold leaf electroscopes. Maybe some of you remember them from school. If you take gold leaf and you simply put it in a bell jar to try and avoid too many air currents affecting the experiment, if you charge that up, because like charges repel, if you've got 2 gold leaves and they are charged up, they repel each other, and hence the 2 leaves separate. If they collapse, that means charge is being lost somewhere. Either charge is being added or charge is being lost from the electroscope. And it was noted that when you charge things up by either rubbing a balloon on your jumper or getting a cat and rubbing it on the ceiling or something, when you charged up your electroscope, it was realized that they would discharge, implying that background radiation is discharging electroscopes. So they had a way of figuring out what background radiation existed in terms of how much, but they weren't sure where it was coming from. Is background radiation primarily coming from below, i.e. the Earth, or is it coming somewhere from above? So it was decided back in the early 1900s, an enterprising individual called Theodore Wolff said, right, I'm going to take one to the top of the Eiffel Tower. I'm going to take an electroscope and see how quickly it discharges at the bottom, and then I'm going to take an identical electroscope and charge it up and then see how quickly it discharges when it's at the top. And if the discharge rate goes down, it tells me the radiation is coming from the Earth. If the discharge rate goes up, it tells me it's coming from above. So what did he find? Inconclusive. In other words, the radiation levels decrease, but it wouldn't be what you would expect if the radiation was simply coming from the ground. And then people said, yeah, maybe that's not a good experiment. Is the Eiffel Tower radioactive? Not a silly supposition. The Eiffel Tower is made of iron. Iron is dug out of the ground. The ground is radioactive. Therefore, maybe the Eiffel Tower is radioactive. So can you actually be sure by taking your electroscope up there? And what about the atmosphere? We know there is a finite amount of radon pretty much everywhere. Not necessarily a lot of it, but it's around. Is that affecting the results? This is where Hess came in. Hess basically said the Eiffel Tower is not high enough to be definitive as a way of telling if the radiation is coming from above or from below. So if you want to resolve the question, you've got to go higher. Very sensible. So he designed detectors that would work in hot air balloons. And in 1911, 1912, he did a series of flights in a hot air balloon to try and work out, does the radiation level decrease or increase when you go up to heights well above the height of the Eiffel Tower? What did he find? In 1911, he ascended in his hot air balloon to about 1,000 meters or so, and the radiation levels didn't really change that much. In other words, there was a little bit of variation, and you couldn't definitively say it's definitely going up or definitely going down. So that's why the Eiffel Tower wasn't good. If 1,000 meters isn't enough, then Eiffel Tower isn't enough. In 1912, he ascended on another flight to 5,000 meters, and at this point, the radiation levels rocketed and increased dramatically. Here we had proof that if you go high enough and get away from the Earth, you are quite definitely picking up background radiation from above. It is nothing to do with radiation coming from the ground. But there's still the question, just because it's coming from above, is it coming from the sun or is it coming from beyond the sun? A very sensible question for any physicist again to ask. So how do you resolve that? Well, you could say fly at night. Do you want to go up in a hot air balloon where you can't see what you're doing, you can't see where you are, you can't see where you're going, and you can't see where you're going to land? Nobody in their right mind would take a hot air balloon flight at night, not being able to see where they are going to land. So you can't take a hot air balloon flight at night to see whether or not it's the sun that is the source of the radiation. So he had a brilliant idea. Fly your hot air balloon on the day of an eclipse. So he went up, he looked at the radiation levels before the eclipse on the assumption that if the moon is blocking the sun and it's coming from the sun, you should see a drop in radiation. No drop observed. It is not coming from the sun, or at least most of the radiation is not coming from the sun. Effectively ruled out the sun as the source of what then became known as cosmic rays, because they were truly cosmic, not simply somewhere in the top of the Earth's atmosphere. If these are coming from above and they're not coming from the sun, these are truly cosmic. And in 1936, Hess was awarded the Nobel Prize in Physics for the discovery of cosmic radiation. So a little less than 100 years in terms of his recognition. So this is an artist's impression of what's going on. It's a rather bad artist's impression for a number of different reasons. What we think is happening is that cosmic ray particles, which will come to the origin of these particles in due course, charged particles are slamming into the top of the Earth's atmosphere and producing a shower of secondary particles. This is a bad illustration, not because it's indicating how many you might get in the secondary shower, that's fine, but the chance you get two showers at the same time, very unlikely, and they're very unlikely to be coming from a very obvious source like that bright star there. So taking that to one side and just ignoring that little artistic license, we believe that cosmic rays hit our atmosphere and produce a cascade, an avalanche, if you will, of secondary particles, which is called an air shower. This is a cartoon of an air shower on the right-hand side. And as a matter of definition, the particle that comes in and hits the top of the Earth's atmosphere is called a primary cosmic ray. And that produces a whole load of secondary particles, far more than the half-dozen particles indicated in this cartoon. It is more likely to be thousands or millions that are generated. But generally speaking, a cascade of secondary particles. Every time one particle hits an atom or hits something and produces a whole load of secondary particles, the energy is shared amongst them. So if you work out how much energy reaches the ground and add it all up, you find the energy of the incoming particle in the first place. And as I've just said, the cascade might produce perhaps thousands, more likely millions of particles, not just the half dozen indicated in this particular cartoon. By the time they reach ground level, there will be an enormous number of these particles. Many of these particles are unstable. They won't necessarily be, for instance, the atoms that were hit by this incoming cosmic ray particle. They are not only going to be, for instance, protons and electrons, though there will be a mix of those in the cosmic rays that you see. Some particles are generated by the impact and are created spontaneously. They are not part of the atoms. They are not part of the incoming cosmic ray. They are not part of the atoms in the Earth's atmosphere. They are generated by the amount of energy with which the cosmic ray, the cosmic particle, comes in.
Can I just ask a question?
Yes.
Please. If you assume that you've got a single cosmic ray coming in at the top, and the total of all the other ones that have collided equal the top one, what happens if, well, I'm sure you'd have more than one hitting the atmosphere at any point in time.
Yes.
Would they then collide with other, and I'm sorry, I forgot what they were called, you'll have to bear with me on that, but so.
In principle, yes, but what is found in practice is that cosmic ray showers tend to occur not overlapping. In other words, depending on the energy, which is what I'm going to come to shortly, it is unlikely that you see a whole load of showers, all of which overlap. There are a whole load of particles hitting the Earth's atmosphere, but you wouldn't expect to get a whole load of showers all overlapping at ground level. So one such particle that is generated by the arrival of a cosmic ray but wasn't there in the first place is a muon. A muon is not part of an atom. It's not part of you and me and every atom in the Earth and every atom in the Earth's atmosphere. It is a particle a little bit like an electron. It's sort of a heavy cousin to the electron. It's 200 times more massive than the electron, and it has no part to play in making atoms, but lots of them are made when something energetic hits the top of the atmosphere. They shouldn't live very long. A muon might only live for a few microseconds, a few millionths of a second, but that's long enough for it to arrive at ground level, go through a cloud chamber, go through the floor, and eventually be stopped by the Earth's crust, perhaps a few hundred meters below our feet. When you work out if it's traveling at the speed of light and it only lives for a microsecond, how can it get from tens of kilometers, which is where these cosmic rays are first hitting the atmosphere and so first generating these particles? The air shower starts tens of kilometers high. In 1 microsecond, it shouldn't be possible for a particle to make it to ground level. It simply doesn't live long enough. But then time dilation comes to our rescue. As Einstein said, when things are moving close to the speed of light, time slows down. So as far as the muon is concerned, although it lives for only a microsecond or two, it still lives long enough to reach ground level. And that is the track of a muon. Here's a picture I took, again, in Blue Peter fashion. Here's a picture I took a long time ago, not a live image. I took a picture when it was on my kitchen table, and I've just tweaked the contrast to make the muon track show up a little more clearly. So the track is simply a whole load of alcohol droplets left in the path of this particular muon. So, as we've seen by what we were looking at and what I was saying prior to the start of the talk, we saw quite a few muons, we saw quite a few electrons, we saw some protons. But what are the primary particles? That's what we saw at ground level. What is it that's actually hitting the atmosphere that causes this shower of particles? So far, we've only been talking about secondaries. And it's taken us a while to figure out what the primaries are. Because either you have to reconstruct what the primary is in the sense of you observe what's going on at ground level and you try and infer what was hitting the top of the atmosphere, or you wait until the space age and then you put a satellite up there and see what's actually hitting the top of the atmosphere. So decades of research has now told us what primary cosmic rays actually are. And it turns out most of them are protons. 90% of the particles that are hitting the Earth's atmosphere are protons, the nuclei of hydrogen atoms. About 9% of them are alpha particles, in other words, the nuclei of helium atoms. And all the remaining cosmic rays, as far as we can tell, the remaining 1% are heavier nuclei, the nuclei of heavier atoms. Which atoms? Well, pretty much the same atoms that we see everywhere on Earth and in the solar system. In other words, after hydrogen and helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, etc., all the way up to as far as you like. All nuclei seem to be represented in cosmic rays, albeit very low likelihood of seeing them. We're much more likely to see protons coming in and a few alpha particles. So let's think about how we detect cosmic rays, both after they've hit the atmosphere, i.e. secondaries down here at sea level, at ground level, and also how do we detect them up there, the primaries. Well, I said before that we can use a Geiger-Müller tube, or what everybody calls a Geiger counter. A Geiger-Müller tube is basically a cylinder evacuated and filled with a gas, an inert gas like argon or something like that. Any radiation that comes in ionizes the gas inside, and because a high voltage is applied to the central electrode compared to the outer casing, any ionized gas, the plus charges go one way, the minus charges go the other way, and so a current is set up, as if you set up a high voltage of a few thousand volts or something. And basically an amplifier, which is part of what's in the yellow box, basically just looks for a sudden change in current and produces an audible click to tell you something has just arrived. Doesn't tell you what, it just tells you something has arrived and somehow it has ionized some of the gas inside the Geiger-Müller tube. What about the cloud chamber? Well, cloud chambers are something like 100 years old, and it started with Wilson, Charles Wilson, back in the apocryphal story, which I guess is probably true, back in 1894. He was on the top of Ben Nevis and he saw the Brocken spectre, the idea that when you look opposite to the direction of the sun, you see under the right conditions on the top of a mountain, if there's lots of mist around, you see your shadow and the shadow of the mountain going into the distance, and you often get these various optical phenomena, these interference effects. You get these sort of rainbows, if you like, around the shadow of your head. He was interested in optical phenomena and he wanted to study them further, but he didn't want to take his equipment up to the top of Ben Nevis every time he wanted to do the experiment. So he asked himself, can I study these optical phenomena of misty conditions with the sunlight passing through the mist? Can I study this in the laboratory rather than on the top of Ben Nevis? So he built himself a cloud in a jar, a cloud chamber, back in 1911. He perfected the first cloud chamber. And it wasn't long before he was doing his experiments, saying, right, what happens if I pass sunlight through this misty cloud that I've made in this jar? It wasn't long before he noticed every once in a while he got a track of a whole load of water droplets forming. He realized after a little while that he was looking at charged particles that were passing through his cloud chamber. Water droplets condensed pretty much the same way that if you've got an aircraft flying at a high enough altitude where the temperature and the pressure conditions are just right and there's enough water vapor up there that the passage of an aircraft will actually condense the water behind it and you'll get a contrail, a condensation trail behind the aircraft. It's pretty much the same idea. If the water is just at the point of wanting to condense, the aircraft can trigger the process. Same idea. If you've got a cloud in a jar, then the passage of a charged particle will trigger the condensation of the water or whatever the particular material is that you're using. As a result, his cloud chambers had a very important role to play in particle physics. Experimentalists wanted to know, if you bang two atoms together, what do you get? If you start looking inside atoms, if you start looking inside nuclei, what are these fundamental particles that make up the world, that make up atoms? Now they had a way to actually see what was going on. Rather than just inferring and listening to clicks on a Geiger counter, now they could actually see particles moving. And if they applied a magnetic field, they could see whether the particle bent to the left or bent to the right, telling you whether the particle was positively charged or negatively charged, depending on the magnetic field that you were applying. And you could see reactions by having particles come in from two different directions and see what happened. In 1927, Wilson was awarded the Nobel Prize for the most original and wonderful instrument in scientific history. That is quite a citation when you think of everything that had come up to the 1920s. So that's just an indication of how important the cloud chamber was in revolutionizing our idea of what is inside an atom and what is inside a nucleus, and this zoo of particles that were being discovered in the early part of last century. So the original cloud chamber has changed somewhat. That's Wilson's 1911 version of it. This is my 2024 version of it. And as I keep saying, if you wish to build one for yourself, the instructions are sitting here on the table in front of me. So I'm not going to deal with the detail. My cloud chamber is a very distant cousin of Wilson's original. He used the expansion of gases to get the right temperature and pressure for water just to be on the point of condensing. I have got a little glass jar and a coaster on the top. A mug warming coaster provides temperature that gets me up to about 35 Celsius, and a little fridge unit, which you can buy on Amazon. Other online retailers are available, will allow you to basically set up alcohol at the top, is heated and vaporizes and then condenses on a cold plate at the bottom. There's a heat sink and a little fan at the bottom just to keep everything nice and cool. So that will allow you to set up the right conditions with alcohol rather than water, because it's easy to vaporize alcohol and it's relatively easy to get it to condense without having a huge temperature difference between the two. So let's switch back. Let's see if it's playing ball or not. Let's switch back to the cloud chamber. So yes, we're seeing a little bit of a pulsation of the clouds. That just tends to be the conditions under which the cloud is forming. You can see the drizzle. Effectively, it's raining, if you like, in the bottom of the cloud chamber. And every once in a while, we will see a nice clear track. Let me just waffle for a few more seconds. There was a nice couple of tracks. There's another one. Let's see if we're going to get another cracking track come through. There's one on the right-hand side and another one on the left. You can see we get a cosmic ray roughly once every second. Some of the tracks are very short because the cosmic ray is coming almost vertically down. It's only when the cosmic ray is coming in at a glancing angle that we see a nice long track. But it happens every once in a while. There was a couple of nice tracks coming through. I think that was a couple of electrons. So let me switch back to the PowerPoint again. So again, just in case it wasn't working, this is a video I made earlier on my kitchen table showing a few different tracks, electrons, whoa, a proton on the right-hand side there, and a few others coming through. I actually recorded something like an hour. You can see one comes through every second or two or three. I recorded an hour's video and then simply added up all of the frames to see how many tracks I actually got. And there were quite a few hundred tracks. There's so many there, you can't really differentiate which one is an electron and which one is a muon. All you can really do is to say the really bright ones, and you can see half a dozen really bright tracks there. They are probably protons that carry a lot of energy into the cloud chamber. But again, hundreds of tracks visible over a fraction of an hour. So how are cosmic ray experiments done by the professionals rather than by amateurs in their kitchen building cloud chambers to see what they can see? Well, cosmic ray experiments were attached to Voyager 1 and Voyager 2 as they flew out of the solar system. I read recently that the cosmic ray experiments on Voyager have just been switched off as of, what, a few weeks back or something? So they've been taking data for the last 50 or so years. And Voyager 1 in 2012 recorded a sudden increase. It was a slight increase or a little bit of background, and then there was a sudden jump in the cosmic rays it detected, indicating that it had left the solar system. In other words, there's a little bit of background radiation coming from the sun, but as soon as you leave the influence of the sun and start flying into interstellar space, you pick up more of the cosmic radiation. Voyager 2 also picked up the same jump, but Voyager 2 is traveling a little more slowly. Voyager 2, if you remember, went past not only Jupiter and Saturn, but Voyager 2 also did a gravity assist from Saturn and went on to Uranus and Neptune. It did a gravity assist from Neptune, but slowed down because it wanted to go over the pole of Neptune rather than get a gravity assist. There was no need to have a gravity assist to make it go faster. It was already going plenty fast enough to leave the solar system. So Voyager 2 is actually traveling a bit more slowly, which is why it took until 2018 to actually leave the solar system. It's heading off in a different direction, but the difference in the dates there is mainly because of the speed of the craft. There's also a cosmic ray experiment on the ISS. It's there on the right-hand side circled. It's called AMS, the Alpha Magnetic Spectrometer. You can get an idea of scale of this spectrometer from the astronaut, who's not necessarily fixing it, but he's there for scale. He or she is there for scale. It's basically not a cloud chamber, but it's a set of trackers that allow you to see what is coming through, give you an idea of the energy of the particles, which type of particle and from which direction. So this was very valuable to give us a day-by-day count of what particles are hitting the Earth's atmosphere. But in terms of cosmic ray observatories, we have got some observatories on the ground where we're of course limited to looking at the secondary particles and inferring the energy of the incoming primary cosmic ray by adding up the energy of all the particles we see in a shower. One of the biggest observatories is the Pierre Auger Observatory in Argentina. There's a number of different detectors. I'll say something about detectors in just a second. But if you want to catch the entire secondary shower, or at least a reasonable fraction of the secondary shower, you need to have a very large footprint, because this starts tens of kilometers high, and it could be a sort of angle that you've indicated here in this artist's impression. So you could have quite a large footprint. So ideally, you want your detectors scattered over a relatively large area. And what they did was pick an area of Argentina where they could basically use a large footprint. And just to give you an idea, that observatory is roughly the same area as Luxembourg. It gives you an idea of the size of this particular observatory. It's a whole load of water tanks. So it's not a cloud chamber in which you hope to be able to see the track of a particle coming through. It's a water tank in which you're looking for a characteristic blue flash as the particle travels through the water. Where does this blue flash come from? Well, the best analogy is to think about this jet fighter. When an aircraft travels through the air faster than sound can travel through the air, what do you get? You get a shock wave, a sonic boom. So what happens when light travels through a medium what happens when a particle travels through a medium faster than light can travel through a medium? Can't happen in a vacuum, but if you're traveling through water or the air, then it's possible for a particle to travel faster than light can travel through that medium. And so you get the analog of a sonic boom. You get a shock wave when the particle travels faster than the light can. And that, not sonic boom, but photonic boom, is this blue flash that you're looking for when a particle travels through water or indeed through the atmosphere. And this little cartoon shows what telescopes are looking for when you're looking for this blue flash in the atmosphere. So an incoming particle will start to produce secondary particles, 2, then 4, then 8, then 16, etc. And as they reproduce and generate this shower of secondary particles, you get this characteristic blue glow, the photonic boom. It's called Cherenkov radiation or Cherenkov light. So this is greatly slowed down because it is effectively a flash. It's a billionth of a second, the length of time it takes for these particles to come through the atmosphere. So this Cherenkov telescope array is a number of telescopes in Chile and a few telescopes in the Canary Islands on La Palma, some in the southern hemisphere, some in the northern hemisphere, and these telescopes are looking to see the blue flash in the sky. They're not necessarily looking for where did the particle come from, they're looking for the flash, and they will then infer where the particle came from if they can see enough flashes in the sky. So there's a whole load of telescopes being built in the Atacama Desert in Chile, a whole load of telescopes being built in the Canary Islands. These are only artist's impression, they haven't got them up and running as yet, but the Cherenkov telescope array is being put together with this in mind. It'll also work in water, which is what the Pierre Auger was doing in those little tubs. They're not hot tubs, they're just tubs of water looking for the blue flash. But it will also work in water even if the water is frozen. It doesn't really matter if the water is liquid or the water is ice. You can still get particles travelling through the ice faster than light can travel through the ice. So they decided to do the experiment at the South Pole, where you've already got ice, transparent ice, that will allow you to do this experiment. So what they've done is basically take a whole load of photodetectors, drill down into the ice. There's the top of the ice pack at the top, there's the Arctic bedrock at the bottom, and if you're having trouble with scale, there's the Empire State Building on the left-hand side there. So they've drilled down into the ice and put a whole load of photodetectors, like a string of pearls, on lots of strings going into the ice. The total amount of ice they've instrumented is approximately 1 kilometre by 1 kilometre by 1 kilometre. Largest ice cube in existence. And that's effectively turning 1 kilometre cube of ice into a detector. If a particle goes through this ice, it'll produce a blue flash, and your photodetectors will then pick it up. The idea being, in this little illustration, if a really energetic particle comes through, it produces a blue flash, and then you see which photodetectors light up. And by looking at which photodetectors have recorded the blue flash, you can effectively work backwards and say that particle must have come from that direction. And depending on how bright the flash is, you can work out essentially how energetic the individual particle was. And if you have enough of these things, you can work out what's going on in terms of the primary. So where do they actually come from? We've talked about these mysterious cosmic rays, these particles, these charged particles that seem to be raining down on the Earth's atmosphere, producing all of the effects that we can see at ground level. But where do they come from in the first place? Well, we should remind ourselves that Edwin Hubble 100 years ago basically told us, 100 years and I think a few months, when was it? November 1924, just over 100 years ago, Hubble said the Andromeda Nebula, as it was known at the time, is not a nebula within the Milky Way, it is a galaxy in its own right. So suddenly the universe got an awful lot bigger when this was realized. The nail in the coffin of the great debate trying to work out what these spiral nebulae actually were. So when we talk about these cosmic rays do not appear to be coming from the sun, they appear to be coming from somewhere else. The question originally was, where do they come from? But now, thanks to Hubble, we realize the question is, are they coming from, yes, outside the solar system, but are they coming from the Milky Way? Now that we know the universe is much bigger than the Milky Way, we now have 1 trillion other galaxies out there. We can ask ourselves, are the sources of cosmic rays somewhere within the Milky Way, or are they coming from another galaxy, of which we now know there are many? The answer is, well, it's a little difficult to tell, but people assume, or at least theoretical physicists and astrophysicists assume, surely very violent events must be responsible if you're accelerating particles to very high energies, which give you the sort of showers that we can see here on Earth. Perhaps the shock waves produced by a supernova, or perhaps the shock waves produced by the jets that come out of supermassive black holes that we see from Hubble and James Webb pictures of various supermassive black holes in various galaxies. Presumably, shock waves are responsible, say some people. but it's not altogether clear what the mechanism must be. Just because you've got a shock wave and a very energetic event like a supernova or a supermassive black hole jet, it doesn't necessarily mean we understand exactly how a particle can gain a great deal of energy. And it looks like some of the cosmic ray particles that are hitting the Earth have very, very high energies. Not all of them perhaps, but some of them definitely do. But shouldn't it be easy to pin down the source? Shouldn't we just say, well, all we have to do is to watch a few cosmic ray events, watch a few showers. Once we've seen a few showers, we can trace back and figure out what is the source. We just have to triangulate back and say, well, you know, it's that supernova that's the source of these things. Or it's that galaxy which we know has got a supermassive black hole at its core. Well, it should be simples, yeah, but it isn't, mainly because charged particles are deflected by magnetic fields. And unfortunately, magnetic fields apparently are everywhere. Of course, the Earth has a magnetic field, and charged particles from the sun end up spiraling in the Earth's field and get funneled down to the North or South Pole, and we end up with aurora. So with low energy particles, things can get caught by the Earth's magnetic field. But high energy stuff should be less affected by magnetic fields. But we still have to worry about not local magnetic fields. What about the magnetic fields in the rest of the galaxy? Or what about the magnetic fields between galaxies? They may not be very strong, but if they exist over many, many, many light years, then even a tiny deflection is going to add up if you integrate over light years, or hundreds of light years, or thousands of light years, or millions of light years. So even tiny magnetic fields could matter. Now, we know how to work out what's going on in a magnetic field. All we need to do is sprinkle iron filings everywhere, and we can see the magnetic fields. Not quite as silly as it sounds, because we can actually map out dust in the Milky Way. Planck, for instance, looked at polarized light, which tells you how dust particles are oriented, and it's thought that dust particles will tend to orientate themselves in the direction of the local magnetic field. But we can see that, well, if that is the magnetic field, it is really complicated. And trying to work out if a cosmic ray particle is coming from somewhere in the Milky Way, how is it going to be influenced by all of these magnetic fields? It's a problem. And not only that, but we haven't got a clue how to work out the magnetic fields in between galaxies. We assume that there is a magnetic field, albeit a rather weak one, in between galaxies over billions of light years. And it might matter, but how on earth do we work out what that magnetic field is? Well, the bottom line is we can't really be sure, so we resort to a piece of physics which says the more energetic the particle, the less it's going to be influenced by a magnetic field. So the low energy stuff is going to have its path scrambled by these magnetic fields. But if we look only at the most energetic particles, hopefully they've traveled in very close to a straight line, and so we can trace back their origin. What do we mean by very energetic? This is just a reminder of what we mean by an energy scale. Physicists use a unit of energy called electron volts, EV. Don't worry about what they are. All we need to worry about is that 1 EV corresponds to the energy of a photon of visible light. And if we go up 1,000 times higher than that, we get a much more energetic photon called X-ray. And we know about X-rays. If we go up 1,000-fold again, we get the sort of energies of the particles we've been looking at in the cloud chamber. Alpha and beta and gamma rays have energies of millions of EV. But cosmic rays occupy the rest of this scale. 1 billion, 1 trillion, 1 quadrillion, 1 septillion, much, 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 much higher energies. Just to give you an idea of scale, the sorts of energies that we can access with the Large Hadron Collider are indicated by the left-hand arrow. And if we ever get round to building an even bigger accelerator called the FCC, that will be where the right-hand arrow is. So you can see that cosmic rays, we believe, are hitting the Earth many, 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 many orders of magnitude more energetically than the sorts of particles that we can build, that we can make in a Large Hadron Collider, which is typically 10 to the 12 EV. Now we think, to the best of our knowledge, if we look at all the particles as a function of energy, the low energy end we think is solar. In other words, the sun does produce some particles, some charged particles, but in terms of cosmic rays, it's very much the low energy end of the spectrum. We think the middle ground of cosmic rays are more likely coming from the Milky Way galaxy. And it is speculated that the most energetic cosmic rays, the most energetic particles, are coming from outside our galaxy. This is by no means a fact. This is more hypothesis that seems to be sensible. But in terms of doing experiments, all we need to do is look at the high energy stuff, and that will tell us where they're coming from. The catch is there aren't many. The red line is how many we can expect to see, the flux of particles. There's a lot of stuff coming from the sun at low energy, 1 for every square meter of the Earth's surface per second. If we go to higher energy, the flux of particles is very much lower, 1 per square meter per year. And if we go to the extreme high energies, lower still, 1 per square kilometer per year. These so-called ultra high energy cosmic rays. But those are the ones we need to look at if we want to get a handle on where are these things coming from. What is the most energetic event in the universe that can produce particles of these extreme energies? A little while ago, there was the so-called Amaterasu event, or Amaterasu event. The telescope array in Utah, USA. It was reported in APOD in 2023. It was recording data, it was relaying or reporting data that was recorded in 2021. Now, the Amaterasu event was the second most energetic particle that was ever recorded to hit the Earth's atmosphere. By the way, it shouldn't be confused with the tiramisu event. That was a completely different thing. The Amaterasu event, the second most energetic particle. And you can see it didn't cover the entire array, but enough elements of the array were hit to be able to work out, if we had picked it all up, what would the total energy be and where was it coming from. In other words, there was enough data to figure out what was the energy, enormous, and which direction it was coming from. So we believe anything that's ultra high energy shouldn't be deflected. So we should be able to trace back the line of sight. So this was done for the Amaterasu event. And when they took the geometry of that event and traced it back on the sky, they found that the direction pointed to, pause for dramatic effect, nothing. There was nothing there. There was no supernova that they could identify that would be the source. There was no galaxy with an active galactic nucleus, no supermassive black hole, which could possibly have produced a particle with this amount of energy. So despite the fact this was definitely one of the best candidates for tracing back where these things are coming from, we don't have enough data. No supernova, no supermassive black hole could be identified. So one of two things: either we just need more data, and if we have a number of these things, if these observatories keep taking data and keep seeing these showers, maybe at some point we'll be able to trace back their origin and see where they're coming from. But perhaps the magnetic fields in the universe are much stronger than we realized, and they are scrambling. Even these high energy events are getting distorted, so it's not coming from that direction. It's coming from a few degrees off, or 10 degrees off, because on its travels from this distant source to us, it's got scrambled by whatever magnetic fields are between us and the source, and we don't know what those magnetic fields are. These particles, including the Amaterasu event, are traveling very close to the speed of light. Remember, as far as a physicist is concerned, speed and energy are almost the same thing. The closer you get to the speed of light, the greater the energy of the particle, regardless of which mass you started with. So we can ask ourselves, just how close to the speed of light are these things traveling? Either the second most energetic particle ever seen, the Amaterasu event, or the most energetic particle ever seen to hit the Earth, which was called the oh my God particle, because when the scientists first saw that, none of the scientists could believe that any single particle could possibly have that much energy. And they've converted the energy back to a speed to give you an idea of just how fast it is traveling, or was traveling. And the oh my God particle was traveling as a percentage of the speed of light, 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 .999999999. We're not done yet. 999. Still not done yet. 999. Getting there. 999. Nearly there. 995% of the speed of light. That's its estimated speed based on its energy, and assuming it was a proton, because that's the most likely particle that it would have been. What mechanism can possibly accelerate a particle, a proton, that close to the speed of light? And the only real way of visualizing it, apart from counting the nines, which is not very useful, let's just think about an imaginary race. Let's think about a hypothetical race over a racetrack of 100,000 light years. Let's just imagine we put a racetrack down beside the galaxy. And we ask ourselves, if we had a race between a photon of light in a perfect vacuum and one of these very, very ultra-high energy cosmic rays, let's just imagine they start on the start line at exactly the same time, and they fly across this 100,000 light years in a perfect vacuum. Now we know that light is going to win. Nothing can travel faster than light. So we know light is going to pass the finish line 100,000 years later. The question is, when light passes the finish line, how far behind it is the cosmic ray that must have lost some ground over the 100,000 light years? And the answer is, the cosmic ray will be behind the light by approximately 5 millimeters after 100,000 light years. Or if you want to think of it in terms of time, if you start a stopwatch when the light crosses the line and stop the stopwatch when the cosmic ray crosses the line, what's the time interval after a race lasting 100,000 years? The answer is much less than a nanosecond. It's actually just a few picoseconds. So something out there is accelerating particles to ludicrous speeds, and we don't really understand what's going on. So the summary: cosmic ray particles are accelerated somewhere, somehow. We don't really understand what, and we don't really understand how. Different people have got different ideas. It is thought that supernova and supermassive black holes are probably sources, but we have no evidence that backs that up. Maybe we're missing something. Maybe they are the sources and we're simply not getting our trigonometry right. But maybe there's something else out there which we've overlooked, which is capable of accelerating particles to these sorts of energies. We know that cosmic rays are deflected by magnetic fields, and we hope that the lower energy ones, yes, they are definitely going to have their path scrambled because they are affected more by magnetic fields. We hope that the really high energy stuff travel in somewhat straighter lines. But given that we don't know what the magnetic fields are, we don't really know. We know that some particles make it past Earth's protective magnetic field, especially the really high energy ones, which hardly know that the Earth's field is there. They just go straight through. And we know that hitting the Earth's atmosphere, hitting oxygen or nitrogen atoms or molecules in the atmosphere, will produce a cascade, an air shower of secondary particles. Some of those secondary particles will make it to sea level, including muons, electrons, protons, and they will make clicks in a Geiger counter, and they will make tracks in cloud chambers. So when we remind ourselves that over a period of many seconds we will see huge numbers of muons and electrons and protons, and when we listen to the clicks in a Geiger counter where the samples are out of harm's way and definitely not contributing to the clicks, those clicks signal the arrival of a subatomic particle that might have started its journey in a supernova somewhere in our galaxy, or possibly in the jets of a supermassive black hole in a galaxy far, far away. In a sense, each click you hear, you're listening to the cosmos. Thank you for listening.